Hello, friends. My name is Shiban. I led teams in the Visual Studio org at Microsoft and more recently led the Cloud Services org at Riot Games. We're the co-founders of a startup called Clotho, enabling teams to write cloud applications and platforms. At Riot, we built the internal platform that runs League of Legends, Teamfight Tactics, and Valorant, serving 200 million players worldwide and hundreds of Riot backend engineers. It took us 120 amazing people, 5 years, iterative shipping, and immense organizational cost. And it was already legacy by the time we were done. This talk is about that journey and how it led Aaron and I to craft a startup around adaptive architectures, the cloud architecture of the next 10 years, helping platform engineers solve one of the hardest, most taxing aspects of platform engineering. Given that we are no longer at Riot, we limited the talk to publicly available information, which you can find references for in the appendix. I'll start by describing the problems that we needed to solve. What were the requirements and constraints that were facing Riot? Then I'll describe how we tackled those challenges when building your platform and platform engineering org. Then we'll walk through adaptive architectures, what they are and how they enable you to power next-generation platforms. If you haven't heard of Riot Games, it is the company behind League of Legends and Valorant, two of the largest games in the world, 200 million players worldwide, #1 and #2 most watched games on Twitch. Stadium-filling esports, award-winning music videos and TV show, $1.5 billion a year revenue, and over 1,000 engineers in the engineering org. Let's look at 7 realities that needed to change and how platform engineering played its role. Red is the reality at the time, purple is the desired end state. Riot had been working on multiple projects, and it was time to productionize them. If nothing was to change, each game studio would recreate in-game chat systems, profiles, developer APIs, and lower-level systems like deployment tools, CI/CD scripts, figuring out scaling rules. And what will shape a lot of the choices that we made is how to ship to Tencent in China. Supporting multiple games meant supporting multiple workloads, whether it's sub-35 millisecond latencies for Valorant, high-throughput APIs, hypercompute for game servers, making sure that databases and the games in general are highly reliable, and being able to burst into the cloud when launching new games versus running efficiently in steady state on data centers. League of Legends' backend is predominantly Java, but different programming languages and ecosystems lent themselves to different workloads, whether it's Python for data workloads, or C# and its alignment with game engines like Unity, Golang for memory-efficient, easy-to-write backend services, or Node for teams writing both backends and frontends where JavaScript or TypeScript made sense. Even if it was possible to stick to only Java, in today's world, to hire the best talent means also having the flexibility for them to use the tools they're already most proficient with. Continuing to build everything for every game meant that game studios would have to hire hundreds more engineers each, which doesn't scale either financially or operationally. Another side effect of each studio working on their own is the limited applicable knowledge sharing across those studios. Building more reliable services, how to iterate quickly, or scaling efficiently. No sharing, no learning. There was also a desire to switch to microservices. It's what the industry appeared to be moving towards, with companies like Netflix evangelizing it and the success they've been having with it. With monoliths, it was easy to bypass architectural guidelines. Let's just ship it now and we'll fix it later, which led to more spaghetti or entangled code. And as League of Legends grew in size, deploying that one large bundle took too much time, and failing could have easily taken down the entire service. So the benefits of microservices sounded very appealing. Riot didn't just have multiple games to ship, but it also needed to ship them on data centers because it was cheaper at the scale that they were operating in. It also needed to ship on AWS for elasticity and flexibility, especially when launching new games, and to Tencent's internal systems for them to operate in China. Cloud technologies were still not converging, and arguably they haven't converged even now. So it was expected that more migrations would happen. So what did Riot build? Riot started centralizing a lot of the infrastructure-related functions from multiple teams into a central platform org. When I left Riot, we were 120 people, 40 working on a container-as-a-service platform, which runs on both data centers and AWS. 50 were focused on the PaaS layer, that's the team that I led, and that layer could target the container-as-a-service layer that our sister team was building, and Tencent's internal systems. Another 30 people focused on connectivity to enable the ultra-low latency around the world for the types of competitive games that Riot were building. Riot aligned on the container as the base unit of compute, and that was important. The Container as a Service group focused on cluster management, automation on Metal and cloud, starting with Chef and eventually using Terraform. They built a custom container and pod orchestration and scheduling system called Admiral, mainly because Kubernetes and Mesos were very early in their development at the time, and a lot of kernel optimizations to maximize the fleet's performance. Platform team built a lot of the components you would need to interface with as a developer to build, deploy, run, and operate applications or game backends effectively. Jenkins was used as the build server, toolbox for visualizing and operating pods, a tool for viewing logs, a tool for setting up networking rules, a tool for interacting with service discovery, a tool for tracking builds, tagging them for shipping or testing, and most importantly, from the developer point of view, an SDK that allowed them to interact with that system, which guaranteed that their code would run the same way on all the target platforms, including in China. It included interfaces for working with discoverers or Riot's Eureka flavor discovery system or configuration system, secret management backed by Vault, and the Elk stack for handling logs and metrics, all wrapped up in a Java SDK. Now let's talk about shipping to Tencent. Shipping a monolith to Tencent was relatively straightforward. Migrating into microservices, however, posed a new challenge. It allowed the many teams at Riot to ship League of Legends microservices independently, but that also meant that they shipped them independently to Tencent, straining the Tencent ops team. Now, with multiple games in the works, it was clear that shipping this way just wouldn't work. That's when the Riot application and environment models were crafted. One or more microservices are a pack or a pod, and a bundle of these are an application. An environment is a collection of applications that work together to form an entire experience. Imagine League of Legends as one application, and the shared game services platform like chat, profiles, store is another application, and support tools as another. The cultural process and technical shift was to move from shipping microservices, or even applications, to shipping entire self-contained complete environments. At that point, the deployment tooling's goal is to transform an environment spec and the application specs into running instances, depending on the target environment. So the League Korea environment had one configuration, which could be deployed on the Riot platform v1 or v2, or a future one. And there was another environment configuration that would produce everything that the Tencent APIs would expect. Same specifications, different targets, run it anywhere. So the platform v2 had a new deployment service based on those specifications. Federated discovery, logs and metrics moved from the Elk stack to New Relic. There was a mechanism to shipping to China and a newer UI that brought together all of the different tools into one coherent experience that focused more on the environment and application level rather than just microservices. Now let's talk about platform engineering landmines. Every team or organization that I've seen has underestimated how hard it is to get an entire company on a new platform. Expect to own both the current system that you're operating while you keep building the new capabilities, tooling, operational excellence, not just for you, but also for the developers using your platform. Developers in the company already built templates, muscle memory, scripts, docs for their teams on which buttons to press to get something shipping. You're going to have to work and fit into their schedules, and that is harder than most people realize. Fast-growing companies hire for total ownership, a mentality that puts speed before collaboration so the company can capture opportunities fast, even at the cost of duplication. Asking teams to align around a single platform and platform team that is almost always underfunded is a bottleneck that they will not appreciate. You're asking individuals that were hired for speed to give up one of their superpowers. Platform engineering needs software engineers. And from my experience, it's rare to find software engineers that love operating things as much as building things. Organizationally, there's a very real scenario where you'll wind up building lots of things and then not have the right staff to operate it. The engineers are also likely to lose interest when the big challenges are solved, leading to lost expertise, putting the same platform at risk as people look for harder challenges. As platform engineers, you won't be building features for the products your company builds. It means that you won't be using the platform that you built the way the developers in the company will be. This gap will lead to major friction between you and the feature teams. Microservices gets harder the more services you have. Triaging is harder, tracing is harder, shipping releases across multiple repos and teams is harder, latency, discovery, failover. The more pieces that can fail, the harder it gets. And turns out that Istio doesn't scale well for your use case. Now you need to convince the entire company to update that SDK that you gave them. Even if the teams agree to it, they still have to roll out these changes slowly and over time, forcing you to maintain two systems, increasing your support burden. And if one team changes their mind, you're now supporting both systems indefinitely. Oh, and repeat this when you want to adopt New Relic or add serverless to the mix. Platform teams sit in between all the teams, and by definition are mission critical. Most importantly, you'll need the company leadership to align on what the company priorities are, because everyone will want you to fix their problems and build their features. If you don't have the company's priorities as input, you'll be building the wrong things, or at least in the wrong order. No one will understand the breadth of use cases you have to support. And because of that, you'll constantly hear things like, just use Kafka. Or if you installed Spinnaker, you wouldn't be building this other thing you have. Teams will only see the world through the lens of their problems and will remain detractors until you solve enough problems for enough teams. What are the themes that we're observing? Whatever you choose, even if it's the right set of tools for this point in time, they will run their course when requirements change. Platforms are about people, and people will ask you to support things they need, rightfully or not. The more you support, more developers and operators you'll need to hire. You will only have a few chances to make large or even small replatforming efforts, even if it's just a small SDK upgrade. And the more successful you are, the harder it gets. So what are adaptive architectures and how do they help? I'm going to ask Aaron to answer exactly that.
Hello, everyone. My name is Aaron Torres, and today I'll be presenting adaptive architectures, the cloud architecture of the next 10 years. In 5 years, mid-sized companies and fast-growing startups won't be developing with microservices. So what is an adaptive architecture? It's a superset architecture that provides all the benefits of monoliths, microservices, and serverless, and it'll do so without having any of the drawbacks of the existing architectures. Specifically, you can change individual components of your architecture from the compute type you're using, in other words, something like EKS or Lambda, all the way down to network protocol, things like TCP versus using gRPC. And it's cloud agnostic, meaning you can target AWS, GCP, Azure, as well as future cloud providers and past services as well. Adaptive architecture solved. Well, first and foremost, it speeds up development. And this is because developers are able to pick a technology or set of technologies and change them later as the requirements change. They're able to adapt their application. It reduces technical and organizational friction for the same reason. Because it's so easy to adapt, there is less of a handshake between the operators, the ones who are going to spin up infrastructure, and the developers who are writing the application logic. Normally, this is highly coupled, and it would require changes on both sides. It makes local development easier because your base application is just a native, normal application on your machine, meaning you can run debuggers, you can run your favorite SDKs and development tools that you would use today without having to compromise. You can scale out application components independently. In other words, you can break out parts of your code that are maybe more compute heavy and need more resources, similar to the kind of benefits you might get in a microservice architecture. It enables repeatable deployments. And by that, I mean, you can very quickly stamp out environments, whether it's going to be global deployments, testing environments, or if you're conducting proof of concepts. It also future-proofs your application because as new technologies are introduced and the adaptive architecture is able to support them, you're able to incorporate them into your app, even if you built and designed your app without knowing they existed. What does an adaptive architecture look like? In our case, the adaptive architecture is a semantic parser on the language that you might be using. So you would write a plain native application. It would read that and compile it or transpile it to support all of these underlying details. So in other words, it can quickly change your original application to be more like a monolith or be like microservices or otherwise. And the lower level details, what cloud you're using and everything else is just an implementation detail. We'd like to solve a problem here, and that problem is that we want a web service that takes an image as a URL and it produces a JSON payload like the one we see on the right. So in other words, it's doing some sort of text recognition on the image, OCR, so to speak, and what we should get back is the URL that was passed in and the text that was translated using our app. For this application, we'll be using this image that we're hosting on the website, which is just a PNG with a gradient, and the text intelligence is the ability to adapt to change by Stephen Hawking. But let's assume you are inheriting this application, and this is the architecture that they came up with. And in this case, it's AWS specific. We have an OCR gateway here, which is an API gateway, and it's able to communicate to 2 Lambda processes. 2 of our Lambda processes are communicating via PubSub, and they're storing and retrieving results in this DynamoDB table called text result. But let's assume your requirements changed. We need to use EKS pods instead. EKS, for those who aren't aware, is Kubernetes running on AWS. First off, why would you want to adapt the architecture from Lambdas to EKS in the first place? How would you do this today without an adaptive architecture? And if you had an adaptive architecture, how would that help you? So why adapt? The first reason is we made the best choices with the information we had. We didn't know that there was a better choice that was going to become apparent down the road. Another reason is organizational change. And this could be anything from an org-wide shift to a technology or platform. It could also be something as simple as teams merging or inheriting a product from another team. Next is changing customer sizes. And this is really a question of the amount of customers you have. So maybe in the beginning, you were under-provisioned and you had way more customers than you were expecting. And so you had to very quickly adapt and change your architecture to handle that. And maybe down the road, you're over-provisioned because you have a lot less customers, but you're spending that money keeping your infrastructure alive. Next up is new technologies or requirements. And this could be everything from someone who's excited about something new and exciting and a new tech that they want to play with, to maybe your latency requirements are much lower than you expected, and the network protocol you chose is just not going to ever work for that scale. You would need to learn a large number of new technologies and best practices. Whenever you pick up a new tech, there's a long learning curve of how you best use that tech. In our case, there's a high likelihood that the original app didn't have anything special going on with VPCs, but now that we're using EKS, you absolutely do need VPCs. So let's assume that you're spinning up VPCs, configuring subnets, security groups, IAM permissions, everything you need in order to wire up that EKS setup. Next, you'd have to reorganize and rewrite your application in order to use the EKS interface, which is most likely going to be REST-based or gRPC versus the Lambda case, which is using invokes, which means you're going to have to revisit inter-module communication, decide ports you're using to communicate between your modules. Next, you have to create Helm charts, YAML specs, Docker things, anything you need in order to make it deployable. And lastly, you need to redo your CI/CD pipeline in order to target that Kubernetes cluster and actually deploy your pods to it. If we had an adaptive architecture, what would this take instead? Well, this is really the whole purpose of an adaptive architecture. Being able to change your compute type from a Lambda to an EKS is one of the minimal requirements for an adaptive architecture. So this should be very simple. It might sound like it would be very difficult to take an app and make it into an adaptive application, but I'd like to show you is it's actually quite simple and straightforward with a tool that we produced. That tool is called Clotho. Clotho is a cloud-aware coding toolbox that allows you to produce adaptive architectures. It does this using 4 simple capabilities. Clotho takes plain code, annotations, and config, and produces, on the other side, transpiled code and infras code. It's transpiled code in the sense that it's still human readable, and it's a version of your code that has been modified in order to work with the infra that we're going to provision as part of the infrastructure as code process. We're going to start with this basic node service for our demo. This is a vanilla node application. It has application level dependencies only. What's not in here is any kind of specialized SDKs, any kind of specs, Docker files, anything related to our app. You can see from the list of dependencies that it's just a vanilla node app. I'm going to run TS node on my main file. You can see that we're listening locally. So this app exposes 2 endpoints. One is a post where you post a URL for it to do the text recognition on. The other is a GET request where you'll get the result from it. In our basic version today, the post version also returns the result directly. And I'm going to be piping this through to JQ to make it print a little bit more friendly here. And what you can see, our original image now is coming back with this resultant URL. It matches the text that was in the image. As a reminder, this is what it looked like. And lastly, if we were to curl the results page version of this, we'll get back the same results as we did on the original endpoint where we did the recognize. If we want to make this a cloud native application, meaning we're deployed to the internet and we're able to hit it from a public endpoint. To accomplish that, we want 2 pieces. We want to bundle our app and put it in some sort of compute unit, in this case, a Lambda, and we want to wire that Lambda to handle requests from an API gateway. So what would this take without Clotho? At a minimum, we would need to modify our Express app to communicate with Lambda, since Lambda is using Invoke and Express is a long-running web service. We would need to spin up the API gateway itself, which would either need to be created manually through the AWS console, or we would need to invest in IAC, either Terraform or Pulumi or the equivalent, in order to manage this in a repeatable way. We would need to set up IAM policies and security groups for all the new pieces, in this case, the Lambda and the API gateway. We have to package up our app in a Docker container and upload it to a registry. We'll be using ECR in this case. And we need to set up a deploy pipeline to take our infrastructure and spin it up and deploy our Lambda to its appropriate place as well. In the Clotho world, we would accomplish this using the expose capability. What it does is it exposes a resource publicly or privately. And that's perfect for us because we had a web server listening on a port, and we would like that to be exposed publicly to the internet. We'll take a look at our index.ts, and what you can see is here is where we're listening on port 3000. Here's the message we saw earlier, app listening locally. And what I'm going to do is I will add the expose annotation to it. The target choices are public or private. We're going with public because we want it to be exposed to the public internet. And I will call this OCR Gateway. And actually, we'll call it OCR Demo Gateway. So it's slightly different from the diagrams we had before, and to show how this all works together. I'm going to transpile our application using TSC, which will take the TypeScript and produce a JavaScript version of the app. And then I'm going to feed that into the Clotho tool, and let's see what happens. After running this, we're given two directories, dist, which is the transpiled TypeScript, and compiled, which is produced by Clotho. Within this compiled directory is everything you need to deploy, run, and operate your service. That means that all of the IAC, this time in the form of Bloomy, but it could also be something like Terraform, the modified version of your source code, plus specs, configs. The thing of interest to us is this OCR demo.png, which I'm going to pull to the side. And this is the topology of your application from Clotho's perspective based on the annotations we've added so far. So in our case, we used expose, and expose told Clotho that we needed to add an API gateway connecting to our compute unit, and by default, our compute units are Lambdas. If you were to run a Plumi up at this point from this compiled directory, it would create this on your AWS account and would return to you a public URL that you could curl. Your app would operate exactly the same as the original local version, only it would be in the cloud. Next up, we'd like to add some persistence to our app. So today, our app is storing intermediate results inside of an ES6 map called status map. Because it's an ES6 map and because we're using Lambdas, it will wipe the map every time that your Lambda spins down or has a cold start. And as a result, maybe we want to make this be persistent. Maybe we want to store this in long-term storage so that through restarts, we're able to persist all of those results. So what we'd like to do is modify our app to store those results in a DynamoDB table called text result. If you were to do this today and generate this DynamoDB table, you would need to create the DynamoDB table, again, IAC or directly through the console. You would need to then pick an SDK to interface with DynamoDB for your application itself. We would like to persist our ES6 map, which is living here in status.ts. So to do that, all we need to do is call persist, give it a name. We'll call this status result because we're storing the results of our status in there. Again, ID is arbitrary name. You can pick whatever you want. And all we're going to do is recompile and see how our image changes. And just like that, now we have status results. This is the point where I want to point out the IAM policies we were discussing earlier. In the Clotho world, these lines represent the boundaries by which these different units can talk. So main can talk to status results. That means it should have the appropriate IAM permissions to do so. You don't need to troubleshoot and start off with an overly permissive model and then reduce it. You get that for free when you compile and deploy. So in this case, only main can talk to status results. Now our requirements changed and we realized we needed to independently scale out certain parts of our compute. In this case, we wanted to separate out the APIs as well as the execution unit, or Lambda in this case, that is doing the image recognition itself. What would this take? It would take quite a bit. And the reason why is because this is fundamentally the first time that we're going from a monolith app into microservices app. So suddenly, rather than supporting one app, we're supporting 3 applications. We would need to break our app into multiple repos or set up hooks for monorepo where different directories fire off different deploy events. We would need to create Docker files for all 3 of services, as well as config and everything else you need to operate individual services. We would also need to set up additional complexity so that services can talk to one another, including service discovery, additional configurations, and other tweaks. And we would need to rewrite all the IACs. So I mentioned before the IAM policies and otherwise, you can see in this how all of those things would change, right? Before you had a single Lambda that could talk to text results. Now there's 2 Lambdas. One of them can't talk to it. There's a lot of tweaks to all of your rules and everything to make this change. In the Clotho world, we accomplish this with a capability called execution unit, which is the smallest deployable grouping of code. And what this allows a developer to do is delineate the boundaries on which their application is split. So they can choose which parts of their program live in one execution unit and which part lives in another execution unit. In our case, we mentioned we wanted to split our routers and our worker itself, the one that's actually doing the OCR. So I'm going to come to our API router. I'm going to come to the very top of the file and I'm going to call exec unit. And what we will call this is API router. We'll do the same on the OCR router, again at the very top, OCR router. And lastly, on our module, we'll call it OCR module, just for simplicity. Recompile. Today, OCR router is importing a function from OCR module, but now they're in different lambdas. So what's happening there? Clotho is translating what was before just function calls in memory to RPC calls. So this is handled all via RPC calls. Again, it handles all the wiring, permissions, and everything you need. But for clarity, what's happening here is now an RPC call instead of just a function call. Now that we've separated out the workflow and we actually have these two paths, one that's writing to the database and one that's reading from it, we now want to make this asynchronous because it no longer makes sense to have the bottom path wait for the write to complete. So what we're going to do instead is when a request comes in through the gateway, we will enqueue it and it'll be read from the exec execution unit to actually do the processing and stored in text results. So for all intents and purposes, these are now independent units. What would this take? You would have to rewrite the transport layer between the lambdas to allow for SNS. You would need the IAC for the SNS. You would need to also set up topics, rewrite the application to use those topics, and you would also have to do a pretty lengthy investigation of how using SNS with lambdas would work, since normally SNS requires a listener. Having a long-running listener on a lambda doesn't make sense. And more IAM rules to tie it all together. In the Clotho world, we have a capability called PubSub, which enables asynchronous message passing. This is the capability that lets you make a event-driven architecture. In our case, is an ES6 JavaScript emitter from the events package that we are able to decorate with PubSub in order to turn it into a cloud-native PubSub instead. So what I'm going to do is I'm going to modify our application slightly to make use of this emitter. What I'm going to do is I'll come to our module, and I'm going to create a listener on this that is going to listen for recognized messages and then do the recognized text that come in. And because this is just JavaScript and it's a monolith application, I'm able to just handle the dependencies by letting the editor autocomplete them for me. Similarly, we'll come down here to the router. Instead of just doing the recognized text, this RPC call, and getting our result, what we'll do instead is we will enqueue a recognized event passing in the URL, once again, resolving the import. And instead of storing the result, which was the translated text, we're just going to stick in recognizing text. So now you have to use both endpoints together in order to get the same result, but now it's asynchronous. And lastly, we'll come back to our emitter itself. And the emitter, once again, is just an event.event emitter. We're importing OCR module here for some JavaScript reasons to let the listen work in that other file. But what I'm going to do is I will decorate this or annotate this with PubSub, and we will call this OCR PubSub. And once again, we will rerun Clotho and our TypeScript compiler to get this diagram here. And as mentioned before, this has all the characteristics we just described. Now, these are no longer talking with RPC, they're talking via SNS. With those steps, Clotho transformed our original simple app into a cloud-native one. But remember, the original requirement is that we needed to reconfigure our app to use EKS instead of Lambdas. We needed to adapt the application. The way Clotho handles this is with our configuration mechanism. So the way you configure an app in Clotho is as simple as this. You can just change your execution unit type, and it will, on next compile, change it from whatever you specified to the new thing you specified. What we have is a clotho.yaml file, which contains all of the application-specific defaults that Clotho generated for us. So this is populated based on the annotations in your application. This is additive, meaning that we can go ahead and delete anything. So in this case, I'm just going to blow away everything but our execution units and some of the front matter up here. I'm also going to blow away these parameters. These things here, memory size and timeout, these are Pulumi parameters, meaning that they're passed through directly to Pulumi, and it would support config that we may not even be aware of because we're not a shim, we're just a pass-through. For our demo, we don't care about these, so I'm going to blow all of these away as well. And we are going to change both of our routers to EKS. I'll rerun the compilation, but this time I'm going to pass in, I'm also going to copy out this clotho.yaml file because the compile directory is ephemeral. I can pass in the clotho.yaml. It will take these, overlay them on the old defaults, and now you can see that our diagram represents that these are EKS instead. This is the total effort without an adaptive architecture, and these bullets are gathered from the previous slides. Something to note here is, although this is already a lot of bullets, some of these, such as spinning up and configuring an EKS cluster, might be another page of this size or more. Not all of these are created equal, right? It's a mind-boggling amount of stuff that needs to be absorbed in order to do this. With our adaptive architecture, from a plain vanilla app, it took 6 annotations and 2 config changes to accomplish that same architecture. Check us out at clo.dev. We are excited to build the community and hear how you like the tool. Thank you very much for your time, and I am happy to take questions.
Yeah, thank you very much. I already see 4 questions that are in the chat. Let's get started from the very top. Is it correct that Riot moved towards more commercial components in their new stack? What was the decision behind that?
So, Aaron, do you want to touch some of that? But I can talk to the time where there's no Riot is a game company. Most companies are not tech companies. If you think about ZipRecruiter, they deal with job listings. If you think about Pinterest, they built a web application for people. They're not in the business of creating tech. And so whenever there's an opportunity to take out things that we have to maintain and invest in ourselves as a company, then we would go and try and replace it if the cost makes sense of transition cost and whatever the new technology can do to own less. Effectively, you have to have less maintenance costs on those technologies. That's one layer. Now, you could move to open source things, but in the ideal case, if you can pay somebody all together to handle a problem for you, like New Relic, it comes down to cost. Like running an elk stack for a lot of data is just a lot of work, a lot of engineering, keeping it reliable. And if somebody comes along and says, you can do this for this much and it's cheaper and less overhead, then why not? Does that make sense, Aaron?
Yeah, I mean, I would absolutely echo that. Like when you build something yourself, it makes sense if it plugs a piece or a gap that you're missing, or that maybe an off-the-shelf vendor doesn't provide. But there's a cost of it, right? And the more custom you get, the more complex it is as you onboard new engineers who are familiar with whatever the industry is doing and are not familiar with your custom version.
Let's move forward to the next question, which looks like a little riddle. I have multiple versions running on antiquated stacks, and none of the original designers or developers are still, and they are so fragile that everyone is afraid to touch it. The company would like to move customers to new platforms, but since the stacks consists of on-prem to private DCs and public clouds, it's so complicated to configure it all out. What do you suggest?
Oy, that's a hard one. Aaron, do you want to start? Because I'll.
Yeah. So I've seen this tackled 2 different ways. The real answer is there's not, like, this is already you're in a tough situation. Like, there's not just an easy solution to get out of it. The 2 ways that I found that have been semi-successful or to moderately successful are either you invest a lot on figuring out what everything is, writing architecture diagrams and having a good understanding, and then sort of start breaking it apart. The other is that you stand up the new version of the stack that is the same requirements as the original version and slowly migrate usage from the old stack to the new stack, right? Like you extract out the technology to something new. Neither of them are easy. Both of them require going back in and understanding the old tech, especially if you've lost people who understand the old bits, especially if it's bespoke to the point of where someone can't even learn it. And it's also very error prone doing that migration to not break users. But like, I think there's a lot of ways to, if you have both things stood up simultaneously, do things like run the same workload through both and figure out where things break and kind of just try and converge to where you solve the same problems with a new stack. And like I said, that's, to be clear, it's like a multi-year effort. Part of why we built this product was to try and make it so that if you invested in this early, it would be easier to not fall into this trap down the road. But if you haven't made that investment, then you have to pay the cost to get out.
Nice. Next question. Guessing you could sub in Terraform or AWS CDK, how does it work?
Yeah, so the idea there is that to us, like whether it's Pulumi or anything else, really, it's a description language, meaning that we have an internal representation of what the architecture is, or architecture as code, which we'll spec out soon and release. But that can be translated into Terraform, Pulumi, CDK, combination. It's all the same. from our lens. The ideal case is that integrates already with your existing pieces too, so it can be included into what you already have. We always assume that you already have a platform of sorts, so you don't have to start from scratch.
Right, and to expand on that for the CI or CD logic using Dagger, yeah, our goal is to integrate with existing tools. There's obviously some nuance depending on how stuff is structured, but yeah, it should be absolutely possible to use that or something like GitHub Actions or any CI/CD.
Yeah, for example, our CI/CD is GitHub Actions, meaning you check into the code with our own services that are Clodo annotated. The next step is to get the CLI, transpile it, the output. We pass it on to the Pulumi part, and it deploys. There's nothing. We tried not to we don't try to reinvent anything that exists in the ecosystem.
How do you determine what was needed and what was possible? Very philosophical question.
So I'm not sure what that means exactly. Can we, Steve, if you can maybe add a bit more context on what you mean by needed and possible? Like how do you take the application and transform it into a specific architecture or like a specific combination of resources? I will assume that for now that's the question. Yeah. There's multiple ways. One is, we are experts in building cloud systems. We follow architectures that have been proven to be useful, but also keep them simple enough for, there's a trade-off between smart and clever versus simple to operate. So we try and create architectures that map well to what the developer intent is, and the operator requirements are. And so we try and keep the minimal amount of sets, but down the line, you can imagine an optimization step or a configuration step where you can change how exactly what gets used. Like, do I want an ALB? Do I want there's actually pieces of that today. Think of them as bundles that can be interchanged.
Next question. What if I have an existing EKS cluster? How can I reuse already existing infrastructure with the new application if I wanted to deploy it onto EKS?
You wanna go ahead for it, Darren?
Yeah, so there's a few bits to this. There's definitely some complexity when you bring existing infrastructure to so there's a question of, do we kind of terraform it to look the way we expect, or do we inject things, or how does that all kind of work, right? And this is true, by the way, for all resources. Like if you have an existing VPC and we want to reuse it, then there has to be mechanisms to do so. I'll say in Kubernetes in particular, we're doing a lot of investment to make this cleaner, and we're working very hard to explore what are the abstractions we're working on. I would say that one of the ways you could tackle something like this, and one of the ways we're investigating, is to try and make it as Kubernetes native as possible. Like the approach we take are the main ways, like installed by a Helm chart, et cetera, et cetera, et cetera. So that when you use an existing Kubernetes cluster, whether it's on-prem or in the cloud, it should look the same, hopefully.
Yeah, but even today, Clodo supports bringing in your own EKS cluster. There may be some assumptions that or some pieces that need to be there for it to function properly, which are documented. Also, you can use custom Helm charts or tack on different pieces. VPCs, same thing. You can have a VPC and basically pass it into the configuration, which then gets used or assume that it's what Clodo needs to use as part of your the generated outputs. So it's not just its own generation. It can take inputs from what you already have. But that's kind of something that we're investing a lot more, especially in the Kubernetes land, where we want it to be more native to how operators and developers already work with Kubernetes.
Nice. Next question. Who builds the underlying code? Pulumi, TF, etc.
Yeah, the two questions down also relates to this. So to be clear, it is absolutely an abstraction on top of Pulumi and Terraform. So in a way, Pulumi and Terraform are one of the target infrastructures or architectures that we are targeting with the compiler. The goal, though, is that in addition to us generating and creating that stuff, we also play nice if you have engineers who write that stuff custom. So if you've already invested in having your own Terraform and Pulumi, our hope is to extend that.
You went through 2 prior platforms before arriving at this adaptive architecture. Do you think a typical enterprise could jump straight to this platform abstraction model, or would they need to get scars and learn the lessons of prior platform iterations and adoption?
If they're open to learning from other people's mistakes, I think, or not mistakes, but the realities of what other people had to go through, kind of the pains and challenges, then yes, I think jumping straight into this would save you a lot of effort and pain because of the ability to upgrade and change over time. It gives you flexibility. You could even use it as a generator. Like if you really just wanted to get started quickly and you don't want to use Clotho, you can describe your thing, run Clotho once, take the output. You don't need Clotho at that point. So there's a lot of different ways to approach this.
How does AWS microservices extractor for .NET differ from Clotho?
I'm not familiar with the microservices extractor for .NET. We can check. I can share kind of what I think or what tends to be different than most solutions out there. A lot of solutions allow you to take a monolithic application and then break it up into microservices. And then you live in microservices land, one way or another. Meaning there's a selection of service discovery and communication, and whether you use this technology or this deployment target, or in our world, one, if you choose to, you can continue writing monorepos and still delineate and split your application. Two, you could work in a meta repo approach where you have multiple repositories, which each one is its own kind of distributed system, and then they integrate together, and then you compile it all together as one larger distributed system. And so you're still working in a monolithic way, but with the output is a distributed system. And then you get all the benefits of the compiler approach, which is you can change different technologies, you can retrofit different services, you can build larger and larger applications without the complexity associated with making it microservice-y. So that's roughly, I think, what these types of tools kind of look at, tend to do, which is basically break things up for you, and then you're back into microservices land.
Yeah, don't brag it. You have a compliment from Frank. Very impressive demonstration. Yeah, sending love to Frank. But the question is, what are the effects of running the update on live traffic from the infrastructure side? Does it support gradual switches to the updated new infrastructures? Is downtime involved, and how to handle it?
Yeah, I can speak to this one a bit. So right now, the thing that's largely handling this bit of it, like how infrastructure has been standing up, is Pulumi, which is our primary target. But the expectation is that as we have more need for this, we'll be able to choose tools to have as deployment targets. And if for example, if you like Spinnaker's approach for how they do something, or if you are targeting Kubernetes can have different deployment strategies for blue-green, et cetera, for services. I would say it becomes much more complicated if you have stateful data. Like if you have a database that already has data in it and you wanted to change that to another technology, that's not something I would just do live without a plan to migrate. But for anything stateless, at this point, it will basically spin up one, switch traffic over, spin down the other. So it's effectively blue-green for non-stateful things.
And this is where you can imagine the compiler, which is open source, gets better over time. Today, it may do a subset, well, but not great. It comes along, we have an idea on how to implement this, or somebody sends in a pull request for a better way to do the switch. You recompile, you get that for free. That's the powerful thing about the approach.
Great. Next question. How do you handle the dependencies between services? I imagine not every dependency lives in the same code package.
Yeah, I think that's where the meta repo comes along. So there's the concept is similar to how we used to build projects back in the day, which is you have a project file which brings together multiple repositories or binaries or projects, and then you reference them. And so what we're working towards is a mechanism for you to be able to create a meta repo, which is a collection of repositories which constitute a workspace, and then a way to reference one another in a way that also works locally. But once you run it with Clotho, it understands that they need to be cross-compiled. And then it wires things through the different code paths We depend as much as possible on the language, understand the language constructs that exist to define relationships whenever possible. Does that make sense?
I think so. They will ask questions more if it doesn't. But I guess Steve added the clarification. So I was asking, how did you estimate or determine what method should be used or works best for your environment?
Mostly expertise at this stage. We are planning on a more, when we go broader with more. So today the compiler has 1 or 2 options or maybe 3 per different target and combinations, which creates a massive amount of combinations, which is part of the problem too. We don't have an automated way to, like, as we scale the amounts of things to today, create the massive matrix of combine everything. And so we try and control for scope for 2 or 3. And based on expertise, I mean, we came from Riot, from AWS, from Microsoft. We have a deeper expertise on what tends to work and what are the best practices around like lower latency, etc. And then we give you the controls with configuration to, we pick defaults, but you can pick what you believe is best. Down the line, what we are planning is a more systemic way of building a cloud model of how each service affects the different requirements or the different runtime characteristics, latency, throughput, cost, and then being able to allow you to set your requirements. What target do you want to aim on those different dimensions? And then the compiler optimizer know how to change and select the right routes all the way down to the architecture on how to maximize that. So that's kind of where we are headed.
PHP support down the road on that road?
Not today, not soon, but I mean, we'll take pull requests and contributions. The thing there is that there's 2 types of there's 2 types to the compiler. There's single execution unit and there's multiple execution units that need to understand kind of how everything talks to one another. It's easier to build out the single execution unit. So if you are interested in like building out PHP support, please join our Discord, chat with us. We're happy to guide you through it. Today we support TypeScript, JavaScript, Golang, Python, C# in different levels of maturity. We'll probably do Java at some stage too. But those are the key ones that we want, again, because of the complexity dimensions. Once we get more people involved and kind of the community contributing, we can expand that.
Right. And to add to that too, we also have some early exploration of things like generating Helm files, which will allow you to deploy any language, but you wouldn't get the benefit of the annotations.
Do you support or plan to support generation of cross-plane manifests?
Not today. It's very much the dimensionality problem is the same problem we mentioned. We are focused on what the customers and users that we work with tend to ask. So if that's something that's interesting to you or want to partner on, let us know. Those are the types of prioritization questions that we tend to like, what do we prioritize first, etc. It's not out of the question. It's a matter of prioritization. But crossplane is one of those targets that we will eventually support or hopefully be supported by the community too.
Nice. On your GitHub page, the adaptive architecture diagram also shows on-prem, either already on solution or implementation directly in Clotho. In some of our customer environments, we are forced to on-prem infrastructures.
Not today. The compiler itself can target custom platforms. It's pluggable. Because of that, or because of the degree of optionality that you get on-prem, you could pick Istio and 7 more things, and Clotho would have to play within those set of pre-selected technologies, and unless we install it ourselves, which most companies try not to, or most you probably won't to do because you already have something. Then that makes the problem much harder for us to tackle early on. It's one of those things where we are open to partnering with somebody and guide them through that process if there's interest, but not today. The eventuality is that it's just another deploy target with custom Terraform that you have built or plugins that you kind of that already use your existing SDKs, etc. They just transform them into, like Clotho would transform its concepts into that pluggable model that you would build.
Cool. Before I read out the last two questions, just a quick announcement that for everyone who's going to KubeCon Amsterdam in April next month, we are hosting the House of Cube party for platform engineers, guys. So please feel free to RSVP. More details coming soon, but I just wanted to share that there is opportunity to party. So you might want to sign up now, but let's get back to the questions. This will also handle anything like network security authentication in front of the application for web-facing applications?
So not to maybe the degree you're thinking, but we mentioned that there's the IAM permission is one layer that we do protected. The other one is where we're placing them in the VPC. So we do have the notion of private and public subnets. So you can be by default, everything is going to be in a private subnet. So it's relatively secured that way. We don't have something like a Cognito integration or some sort of auth layer yet. It's definitely something we can investigate, but it hasn't been an investment yet.
Now, keep in mind that, like, let's talk about WAFs or firewalls. The way this is designed is for you to be able to integrate existing infrastructure as code into this. So you could set up your own WAF using Pulumi or Terraform, and then attach the objects, let's say the ALB or the API gateway that Clotho produces, and bind them without any special thing, because it's all infrastructure as code. So you can basically say, I'm going to create this WAF, you don't even know about it, and here I'm going to attach it to this API gateway that Clotho produces. And that's the mid, kind of the layer where we want you to be able to use. We don't want to bottleneck you or force you to only use the things we support. That's the pluggability, one of the pluggability models.
We already have 19 questions answered. Good job. But we have two more. As I understand from documentation, Clodev currently supporting the AWS and GCP platforms, and mostly pointed on microservice architecture. So what about Azure Cloud and legacy stuff like VM support?
Azure is probably the next cloud we'll support. And we have talked about VMs, like, it doesn't have to be containers. It doesn't have to be like, to us, it's just another target. So VMs will come down the line, ideally micro VMs too. But it's not currently, it's not the top most priority. Azure will come in probably once we want to look at another cloud support system. So if that's interesting, please do join us on Discord, reach out.
Cool. How confident are you that Clotho and its successors is supported, maintained from Riot or preferably its own community in 5 years? Do you need a certain amount of traction to invest more time into it from business side?
Right. So Clotho is, while a core of it is open source, it is a startup and it is funded. We've been around for a year and a half. We've been working on the tech for 2 years and a half. It is not a Riot project. It's been in production for a year with multiple companies, and we're onboarding more now. And so it is not just a community project. It's very much a supported business.
And the last one is just many compliments. Thank you so much, guys, for the webinar, for the tool, and I don't know, anything else from your that you would like to add from your side, because we are gonna send out the webinar replay tomorrow to everyone who attended the webinar. So you'll have the replay and can watch it, send it to colleague. Read and register for House of Cube Cup party if you are going to Amsterdam. Excited to see you there. Other than that, hope everyone has a great end of the day or just the beginning of the day. Never
Perfect.
know.
Yeah. On our end, we are clo.dev. Check it out. Try it out. GitHub. Join us on Discord. If you're using Kubernetes, we're going really deep on Kubernetes now. So please reach out. We would love to, find us on LinkedIn, find us on Discord, whatever works. We're happy to chat. Thank you for hosting us, Maria.
Thank you. On platform engineering Slack, you forgot.
Absolutely. We are so that's a good point. We are on the Slack, the platform engineering Slack. You can ask us there in the channel too. We'll probably go there right now and check if there's questions or people want to chat. Happy to.
Exactly. Cool. Thank you so much, guys. Have a nice day. Bye.
Thank you.